Nice to see so many of you here. My name is Johan Andren. I work on the Akka team at Lightbend. So Lightbend is the Scala company. But we also have Akka and Play framework you might have heard of, and this microservice framework thingy called Lagom. I also co-organize the Scala user group in Stockholm. And to be honest, I'm like a little bit nervous because when I came here, I kind of noticed this. So I just wanted to remind you that, you know, if you have a gun, maybe you can just give me a bad rating in the conference app instead of using it. Thanks. Okay, so can I do a small poll just to know who I'm dealing with? How many of you have heard about Akka before? Okay, and how many of you have actually used Akka? Okay, not so many. Yeah. Okay, good. So Akka is a toolkit for the JVM that means to make it easy to build reactive and concurrent and distributed systems. There's a fancy list of big companies using Akka to build such systems. And inside of the toolkit, there's a few different things. So we have actors, which is like a model for concurrency, kind of originally made famous by the Erlang programming language. And then we have, on top of that, cluster and remoting to build systems that span many servers, like when you need to scale out or you need to have high availability and be able to cope with nodes going away, crashing, someone pouring coffee in the server by mistake, things like that. And then we have persistence, which is making actors survive a crash and kind of get back to the same state when you start the system again. And we have a fully synchronous streaming HTTP server and client, which is called Akka HTTP. And all of this is written in Scala because we really like Scala, but we are very careful to make sure that there are Java APIs for every feature. So there is some things you cannot express in Java that you can express in Scala, but for every feature in Akka, you can use them also through a Java API that makes it nice and more Java-like to use. So today we're going to kind of focus in on one of these modules, which is Akka Streams, which I very cleverly jumped over when I went through the list. But before we do that, I'm going to give you some background. So how many of you have heard about reactive streams? Okay, a few. So in 2013, a bunch of people, among them a few team members of mine, got together and decided that there needs to be some kind of standard or generic API for asynchronous back-pressured streaming to happen between libraries, so that you could provide like a database driver that could stream stuff and you could consume it from a library that isn't written specifically for this database driver, for example. And there was some work and there was some early implementations already in the beginning, and Akka Streams is one of them. And in 2017, the APIs got included in Java, so it's part of the standard library now, JDK 9, since JDK 9. And there's some stuff in the JDK that is also kind of adapting to this, places where streaming makes sense. That is happening right now. So like the mission statement for reactive streams is that it's supposed to provide a standard for asynchronous stream processing with non-blocking back pressure. Let's just kind of zoom in on these different parts and see what they actually mean. Let's start with stream processing. So now I already snuck in kind of a few concepts from Akka Streams that isn't really reactive streams concepts. So we have a potentially infinite stream of elements that we want to process somehow. So we have a source of those elements, and then we have a processing stage that wants to transform them some way or filter them or do some kind of processing. And then in the far end we have a sink that is kind of the end station where all the elements will end up. So this is kind of the stream processing part. I think most people kind of have a gut feeling for what it is. And the next part, the asynchronous part, it means that between each of these kind of stages or operations, there can be an asynchronous boundary. So each of these three things can be running in a separate thread. They don't have to, but they could. And then the final part is the non-blocking back pressure. This is like something that needs a bit more explaining, I think. So imagine that we had a producer that produces 10 messages per second, and then some kind of transformation, and then we have a downstream that cannot consume messages at a higher rate than 1 message per second. Since we have an asynchronous boundary, we're passing elements across to a different thread. There isn't really a way to make the sender not send more than you can deal with, right? So we will end up with something filling up. Worst case, the heap and the JVM crashing with out of memory. Or we could imagine that we introduce a buffer, and when we get more elements than this buffer can fit, we start dropping elements. So we throw away the oldest, or we throw away the newest element, which is also not an amazing solution to this problem. In some cases you could do this, but in many cases this is not what you want. So what this asynchronous non-blocking back pressure is all about is sending demand upstream. So if our sink in this case has space for 2 more messages in its buffer, then it can ask for exactly 2 more elements from upstream. And this is passed on all the way to the source. So the source isn't allowed to emit elements at a higher rate than the downstream can deal with, right? So we're basically controlling the producer from the consumer side. And this is the whole concept of reactive streams, the most interesting part. So the purpose of this reactive streams API is to provide an interface between libraries or frameworks or toolkits. It's not so much for consumer code. And if you look at the rules around these APIs, like the APIs are deceivingly simple and easy to kind of grasp, but then all the semantics, the concurrency semantics around them is quite complicated. And there's a whole TCK that you need to run when you implement something to make sure that you got it right. And there's another talk in this room, not directly after this one, but the last session this day, which will, I think, dive deeper into reactive streams and how the APIs look and all that, if you're interested. Okay, so let's go back to Akka Streams now that we have kind of set the stage. So, optimistic 20 seconds run through of Akka Streams APIs. We have some boilerplate that I'm not just going to skip in the following examples, but you need an actor system, which is like the thing that the Akka runs stuff inside of. And then you need to create a materializer. So the materializer is what kind of runs a stream. And this you need to pass to your stream that you have described. And the actual API for describing the stream works like this. You define a source, and the source has a type parameter which kind of aligns and makes sure that you cannot combine stuff that doesn't know how to deal with what is coming from upstream. So we define a source, and then we define a flow in this case that transforms numbers into strings. So that will give it the type parameters integer and string. And then in the far end of the stream, we have a sink that accepts strings, right? So you can see how you have described what your stream is doing. Same thing in Scala. I'm just not gonna talk about that, but just want to show you. The APIs are very similar. And of course, like this is such a simple thing. I just want to stream a bunch of numbers into something that makes strings. So there needs to be like a nicer, simpler API for this. So this is kind of more of a builder style API. And what you're actually defining until you're calling a method that has run in it is like a blueprint. And this blueprint for a stream, you can run it several times. So you're not running the stream, you're defining how the stream topology or the stream layout is. And then in the end, you can even hand that to someone else who will actually run it. So this means that you can also provide small sections of streams that other people can compose into more complex streams, right? Same thing in Scala. So let's look at something more realistic. So this is my startup project, Numbers as a Service. So it's a complete HTTP server that will stream from 0 to the maximum integer value. So we start with defining a source that will stream from 0 to integer.max value. And then we map each of these numbers into a byte string. Byte string is like a wrapper for a byte array in Scala, in Akka, to make sure that we have like an immutable array of bytes, which is then safe to pass between threads. And in this case, we also add a line feed in the end to get nice output if we browse to this route. And then we define a Akka HTTP server route. So this will accept requests for the path numbers. So if you browse to it, you will go like /numbers, and then we accept a get request. And when we get a get request to numbers, we complete it with this response that we're creating. And the HTTP status of the response is OK, so 200. And then we give it a body that actually is a stream of bytes. Okay. And then to be complete, we take this route that we just created and we bind it to a port on our machine. And then some extra boilerplate just to print a bit if something goes wrong, or if we bind successfully, we get some standard out. And the same thing in Scala, also very, very similar, but maybe a bit less codey. So this will actually lead to, when a client connects, if the client is slow, this will mean that the sending buffer on the server will fill up for this connection, because TCP also has back pressure. And when the client buffer will fill up because the client isn't accepting fast enough. And that will lead to the server back pressure, the server filling up because the window doesn't move forward with the TCP. And this then maps into back pressure inside of Akka Streams. So this means that our number generator on the far end, the speed it can emit elements is controlled by how fast the client is. So without us really dealing with this like low-level concepts at all, we get this as a freebie. So let's look at a more, maybe even more realistic example. It's actually based on a blog article by a guy called Colin Breck, who has written a few very nice things about using streams and Akka actors. And in this case, we're pretending that we're building some IoT thing. So we have some form of little machines that will send us sensor events over WebSockets. And the flow of these WebSocket events is what we're looking at here, the measurements flow. And the first step, the flat map concat, is a bit of boilerplatey thing to deal with the fact that WebSocket messages can either be like a single strict chunk of bytes, but one WebSocket message can also be a stream of things. So it's a part of the WebSocket specification. So that makes it possible with WebSockets to stream like a really large file as one message without doing any kind of chopping up in smaller parts yourself. But in this case, we just want to, if we get a stream of bytes, we just want to concatenate those into a single string in this case. And then we want to make sure, we're going to write this to a database, but we don't want to hit the database for every event that we get, because we would overload the database. But instead, we want to make sure that if we get peaks of messages from a client, we want to collect those and write those to the database in a batch. But we also want to make sure that if the server crashes, or if there is just very few, if there isn't a peak, if it's the opposite of a peak, so we get just one message, one event from the sensor, we want to make sure that that is also. So this is what the grouped within does. So it will collect up to 1,000 elements, the first parameter, or at most for the duration of 1 second. So if it reaches 1,000 elements coming in, then it will write to the database. Or if a second passes and there was just a single or two elements coming in, we will still pass those downstream. And then the next step is a pretend database that we're calling. So we have a async bulk insert method that returns a completion stage. So something that the database completes when it's written something to the database. And we want to make sure that we can accept like a few of those happening concurrently, right? Because throughput. But we want to get the results out in the same order that we trigger the writes. So this is what the map async does. It takes a parameter for how many elements it will process concurrently, even though not all of them has completed. And then the final thing is that we transform the response we get into a new WebSocket message to send back to the client, some form of an acknowledgement in this case. So this is just like I said before, this is like a blueprint. It defines how a stream will be, but it doesn't run anything. So to actually use this, we will plug it into the Akka HTTP routes API and the handle WebSocket messages method. So when we get a GET request to the path measurements, very much like the previous sample, instead of responding with just a regular HTTP response, we connect this request into, or upgrade it into a WebSocket interaction, which is like a full duplex, kind of, we can get stuff both ways. And we give this blueprint to it. So every time there is a WebSocket connection like this, there will be a new instance of this stream that is started and running. And then the same kind of binding stuff in the end. Yeah, and then the same thing in Scala. Also, the difference isn't really that big. So, let's talk about pancakes. So I have two teammates who have different opinions. Actually, they're not. So Roland used to be the tech lead for Akka team. He's not in the Akka team anymore, but Patrick is the current team lead. And they have different opinions on how you should make pancakes. So setting the scene, we have a source of batter, like the mix that you make the pancakes off, and it streams downstream in scoops. And then you have like a frying pan that accepts a scoop of batter, and it fries a pancake, and then downstream we have pancakes passing on to Hungry Sync, which is like one of your kids or a friend who really likes pancakes. And Roland, he really likes to pipeline his pancakes. So he likes to have two frying pans where he pours a scoop of batter in the first one, and then he fries one side, and then it takes it over to the next frying pan and fries the other side on the next frying pan. And at the same time, he can fill the first frying pan with the next scoop, right? So it's like half frying two pancakes at the same time concurrently, or in parallel, sort of. This is nice when you have a problem where you can split it up into like smaller portions of work that depend on each other. It's not so nice if you have like one task that takes a lot more time than the other one. So imagine that the first frying pan would take, 20 seconds, but the next frying pan takes just 2 seconds. Then the second frying pan will be empty most of the time. So it's better when you have portions of processing that takes essentially the same time. And this, if you would write it in code, it would look like this. So we have the frying pan 1, which is a flow of scoop of batter to half-cooked pancake. And then we have frying pan 2, which is half-cooked pancake to fully cooked pancake. And then we combine those into a single stream that accepts scoop of batter and produces pancakes. So one thing we realized pretty early on is that having asynchronous boundaries between stages, operations, like automatically introduced, it very seldom helps with performance. So what you want to do is to explicitly say which parts should have asynchronous boundaries in between, which parts that can run on different threads. So this is done like in the last row with the async method. So we're saying that after frying pan 1, there is an asynchronous boundary. And then after frying pan 2, there's another asynchronous boundary. And this means that the elements will be moved between, be passed on, but the first frying pan can start on the next thing coming from upstream. Same thing in Scala. Patrik, he likes to cook his pancakes in parallel. So he will actually have 2 frying pans and he will pour a scoop of batter in each and then fry the pancake until it's half done and then turn them over and fry it until it's completely done and then move those on to the plate. Right? So there is some form of balancing going on. He's deciding kind of where to scoop the next scoop into, and he's also kind of merging the result onto the same plate somehow. This is really nice because it easily kind of scales up. You can just make more of these parallel, you can buy more frying pans, right? But the problem with it is that it doesn't keep the order. So if one frying pan is like slightly slower than another one, then the outcome won't be sorted in the same way that the scoops of batter came in, which is maybe not so relevant for pancakes, but maybe that's not what you're really working on in your day job. So this is how this looks in Java, and here we have to kind of move over to a different API. So what I have been showing you up until now was what we call the flow API, which looks a bit like a builder thingy. But here we have like separate branches, like a graph with separate branches. And this isn't really convenient to express with the flow API. So then we have to move over to this graph DSL API, which is immensely more powerful, but you shouldn't use it unless you really need, because it's also quite a bit more complicated. So in this case, we're creating the merge and the balance as 2 separate things, right? So the balance is the scoops coming in, getting assigned to a frying pan, and then we have the merge on the other side. And then we create 2 instances of frying pan. So in this case, this is another example of the flows being a blueprint, right? So we define the frying pan only once, but then we put 2 of them inside of this flow. And this is maybe the example where Scala shines a bit more, because here we have possibility to do more tricks. You could also imagine that these 2 guys decided to work together instead of against each other by doing like a parallel workflow where you do pipelining inside of the flow. So you could have 4 frying pans where you fry half in frying pan 1 and then the other half in frying pan 2 if you put the scoop in that branch of the graph, so to speak. So this can also be like an interesting combination for some workloads. There's a ton of built-in stages. Like this list is dated. I think I created this list a year ago. So there's a bunch of more things, but already then it was immense. I would say that there's probably like a few of them that you will need to know, and that will be the ones that you reach for. But there's a lot of stuff that when you dive into specific problems, they become more interesting. Like the take while that I showed you before, which kind of buffers within a limited time range. Okay, so you like this API and you want to connect things which isn't covered by this set of predefined stages. So for this, we have kind of a branch project called Alpaca, which is a community to make connectors for different technologies. And we just got staffing for this, actually. So before it was a purely open source community-driven project, but now we have 2 people working on it full time. And in Alpaca we have also a dated list, but in Alpaca we have connectors for Cassandra, AWS stuff, different message queues, JMS. Yeah, so you can use Akka Streams together with Alpaca to stream stuff from your FTP server and transform it and then put it on your JMS queue or whatever. In addition to like the basic stuff that is already inside of Akka, which would be then like a TCP server client, streams, and interacting with actors, other reactive stream libraries, Java streams, input-output streams, file I/O. Okay, but what if you're like this super special snowflake who has the waxed mustache and the neck tattoos and the whole kit, and your problem is so unique that no one has ever solved it before? It might also be that you're a very sad Java developer who has to integrate with some really legacy thing that no one else wants to integrate with. So for this we have like a third API, which is called the graph stage API. So all of these stages that you have seen in the previous samples, they are built using this API. So this is like the lowest level building block of Akka Streams. And a graph stage is defined by extending the class graph stage. And it takes a type parameter, which kind of describes what sort of stage it is, if it is a source, if it is a sink, or if it is a flow that takes elements and emits elements. And there's a few more shapes for more complicated things where you have fan in or fan out or M-to-M kind of in and out. And to fulfill this, implement the abstract stuff on this graph stage, you have to define an inlet and an outlet that matches the type. And in our case, we're gonna make like the simplest stage there is, which is map, right? It takes elements of type A and then it applies a function to them, and it gets elements of type B, which it passes on downstream. So to do this, we take a function f. So someone else is actually defining the actual transformation. And then we create a inlet that accepts A, and we create an outlet that emits B. And then we make a shape out of those. And the shape is what we need to return to kind of fulfill the API requirements. So this is like the blueprint part of it. And when a stage is actually run, it's going to lead to this create logic method being invoked. And the create logic method, it will create an instance of graph stage logic. And inside of this, we have like a guardrails thing going on. So whenever there is demand from downstream, we will get a call to on pull. And we can deal with that somehow. We can, in this case, we just pass it on upstream because we don't have any internal buffers, or we don't want to kind of do any tricksy stuff here. We just want upstreams to pass us an element so that we can transform it. And then upstream is going to push an element onto us. So we get a call to the onPush method here in the abstract in handler. And to get a hold of the actual element, we call grab. So we get an A, and then we pass this A instance to the function f that we took to the constructor of the blueprinty thing. And then we push the result of that downstream. And Akka Stream guarantees that you don't do this wrong. So if you try to pull twice, for example, without getting an element in between, you will get a nice error message saying like, an exception that says like, oh, you pulled twice on this input. That is not allowed. Okay. Same thing in Scala, also just pretty much the exact same, I would say. Okay, so when does this, when should you use this instead of other things? Well, if we make like a very unscientific graph of how complex different abstractions are compared to how many use cases they can model, then we have like the completable futures, so completion stage in Java and futures in Scala, promises, those kinds of APIs. They can only model something that, a result that will be here at some point or fail. So they're kind of limited in complexity, very easy to understand, but they also can't model many things. Streams would be like one step up because they model a potentially infinite stream of elements that aren't here yet and that can fail at some point. Actor is like far out there on the modeling power side because they can model distributed systems, which none of the other kind of concurrency abstractions really do. And then we have Java concurrency, which is, just bananas. You can model anything you like, maybe locally, but, the headache you're going to get is just, there's no end to it. Okay, but what about actors and streams? Are they kind of mutually exclusive somehow? No, you can actually put an actor around the stream to encapsulate it, to monitoring it, to make sure that it restarts if it fails and things like that. Again, a really good article series by this guy, Colin Breck, that I can recommend if you're interested in that part. Okay, but what about streams in a distributed system? So streams is like a purely local abstraction in itself. It's something that you run on one JVM to define this kind of stream. And then you might connect it to as a server or to a client of some kind that goes over network. But since you can wrap them in actors, you can easily, for example, shard them over a cluster and run a subset of elements through the stream that is running on one node and make sure that you always have a stream for a particular shard running and things like that. We also have something new since Akka 2.5.10, so since early this year, I think it was, which creates a stream that has some networking in between. When you run it on a cluster, you can stream stuff between nodes in the cluster. And how it works is that you define your source and then your regular flow stuff, and then you feed that into a special sink. And when you run the stream, you get a source ref back. And this source ref you can send over to another node in the cluster. And on that side, you can then combine it with a bunch of stages and then run that side of the flow. So this will give you elements flowing all the way through the local processing on the first node and then across the network and then inside of the second node. And the sink on the second node is what will kind of determine the pace that element can be emitted in the source, just like with all the other stream stuff. So it's still back pressured. I have some code showing this, but it is Scala. Yeah, let's just not go through that. It's not complicated, so it's just a special sink and you get a source back and then you send it somewhere. And then on the other side you get it and you combine it with other graph stages and run. So this is by design not kind of meant to compete with big data streaming, things like that, because they all do automagic, you just define some form of stream processing like Think or Spark, and you put it on a cluster and it automatically kind of spreads the work. But in this case, you actually have to be the one who decides where things should run. So it's just the option to flow stuff between nodes that it provides. So it's really great for if you already have a cluster and you want to connect this JMS thing and do some processing here and then, consume it somewhere else to put it in, publish it as a HTTP endpoint. I don't know. So we have a very active community. I think like any given 3-month period, we have like 200 people active contributing issues and pull requests with features and improvements. So if you're interested, we have very nice forums where you can ask questions or help other people. We have, if you're more into kind of real-time chatty stuff, then we have a Gitter channel for users, which is called Akka/Akka, and we have one for us who work on the actual library ourselves, which is Akka Dev. We have marked up tickets in our issue trackers with this easy to contribute, and there's also one called nice to have low prio, I think. That might be a good starting point if you would like to make a contribution and contribute to Akka. Okay, now I did this much faster than I thought I would. So, does anyone have any questions? I think there is a microphone coming so that it gets on the recording.
The question is that you basically ran very fast through the most interesting point, which is how multiple Akka nodes share the tasks. So because the API is basically similar to other reactive frameworks like Reactor or RxJava, but this is a very interesting point. So maybe you could elaborate more on that.
Yeah, so one example for this is how it's used is with these persistent actors, and the persistent actors are event source. This means that every time there is a change in the actor that is modeled by accepting a command, so a message that is a command, do this, it's transformed, validated, and then transformed into a domain event. And the domain event says this thing happened, and you write this to the database, and you get an acknowledgement that it was written, and then you can apply it to the state, and you will know that if there is a crash during this time, the actor will replay to the state where it was the last time, right? So for every change in the actor, there is an event in the database. And a very common kind of use case for what you were asking about is the read side of this. So often when you do event sourcing, you also want to do CQRS, right? Command query responsibility separation. So you have one side that is responsible for your writes, that is optimized for that. And you have one side, or many sides, that are responsible for different kind of query capabilities, right? So it might be, something more complicated than just the current state. It could be like the state over time, for example. And you don't want to keep that in your source of truth, like the state of the thing, like the user or the ticket sales system. You don't want to keep also the history in the side where you decide if you can sell a ticket or not. But that is interesting information. So for this read side, we have Akka persistence query, which is also stream-based. So what you get is like a stream of events that you can then transform and write into a database. So super common use case, and you use it because you want to scale out. So you want to have these actors in memory rather than hitting the database for every kind of interaction. But if you want to scale out, then it might also be too many events to just have a single stream where you consume them and write them to a relational database or something like that. So in this case, you can use sharding. So sharding is something where you would use it for the write side to start with, right? You would shard over the ID of the user or the customer cart or whatever, so that at any given time you can add nodes to your cluster, and the domain objects, they will be spread out over the nodes. So if you remove nodes, they will be, brought to live on a node in the new smaller cluster. But you also probably want to do this on the read side. So this is what the example. I have so much animations, I don't dare to go there in the slides, sorry about that. But so you might want to then just consume a subset of these event logs on each node in a cluster. And if you want to kind of get deeper into that side of things, Logom already kind of encodes this. So there is sample code or actual code in Logom that does exactly this. But what you do is that you decide on a number of tags that you also write in the database with the persisted events. And then you create streams of events for one specific tag that you can consume that is like a subset of all the events. And then you use sharding on that side as well to keep a consumer alive in the cluster at all times, but also to spread out those consumers across the cluster. That was a really long answer and not maybe on point, but okay, great. Any more questions? There is no stupid questions.
I would really like to, but I understand it's not easy to go back a few slides. So you talked when you want to write on the result on a database, and you have a time threshold that says, okay, if in this 5 seconds I don't get any connections, I will batch all writes there. But what if the connection is broken? How does the API react?
So in this case, there was no logic dealing with failure of any kind. So in this case, they would just fail the stream, right? And that would fail the WebSocket connection to the devicey thingy that we made up. So in an actual system, you would want to deal with failure somehow, very likely.
And does this framework have like something to wrap up? I don't know.
So you would likely make that failure handling not inside of the stream, but in the database connection thingy, right? Maybe encapsulate retrying or something like that.
Oh, okay. Okay, so I have some pool and I get the connection. I'm supposed to be okay if I get the connection from the pool in order to write.
Yeah, and maybe if it fails, you will do some back off and retry and up to a specific limit, and then you actually fail it, right?
Okay.
Maybe you said something about it. But how do you do to deal with the ordering? Because I'm having in my customer, they have this kind of technology, but it's homemade, and we have struggled with the order when we are using load balancer and the balancing. How do you actually deal with that?
So if you would put a load balancer in front of it, right, you would bind HTTP to 5 nodes and you put a load balancer in between, you will have the same problem probably as you're having.
So we ended up to say we go always to this node with that, but it's not a good solution.
Yeah, and I mean depends on what in your business case, what is the right ordering, right? And that is always complicated with distributed systems. As soon as you have more than one node, who came in first, or if you're going to use timestamps, it depends on if all nodes were really tightly synced with their clocks or not. And
they should, I don't know. And we have this because we have it's a new product, and then it's coming a change always immediately after it. And then if the change is coming before the product, then we have a problem. So that is actually the node problem we have.
I can't say that I have a kind of
but it's
a black box solution, but in many cases you can introduce like sequence numbers on the sending side, for example.
and then
So
just-
if you're wanting to identify ordering from one client, right, you make that client have a counter. Every new message you up it with one, and then you put that in the message that you send. And then on the server side, you will have the ability to know which was created first, basically, right? But it's not the solution for all problems like that. So